Okay, so let's read at another result in Mileti's textbook. So we are in page 66 on Mileti's textbook. So this one is with Koenig's lemma. Here is the intro, the motivation for the result. And let's start with the definition. So we say that a set T in 0, 1 star. 0, 1 star, we haven't defined that in class, but we defined a different notation in class. I think we define 0, 1 to the less than omega. And again, that means you have to kind of look back in the textbook and see what 0, 1 star means, where it's defined. Somewhere there, you'll see that it's the same as this, which is a set of all finite tuples of zeros and ones. Okay, so as a set of tuples, a set of tuples is called a tree. We are defining the word tree, and this is the property. Whenever sigma belongs to T and T tau is less than or equal to sigma, again, have to look back in the textbook, what does it mean? And it means there is an initial segment. As a tuple is an initial segment of the other. Okay, so it's a substring. So the tuple sigma starts with the first few bits are tau. For instance, if sigma is 0, 1, 0, 1, 1, 1, tau maybe 0, 1, 0, and it'll be a substring. Okay, so also always think of a particular case to see if you picture where it is. And then it says, well, okay, if you have sigma in T and tau is a substring, then we have tau in T also. Okay, so, and here it says, for example, that thing is a tree. Okay, so for that to make sense, I mean, you look at it and you can say, well, let's just check on the definition. And you say, well, this guy is here. If this one is sigma, what are the possible initial segments? The possible initial segments are 0, 0, 1, 0, and 1. They're all there. Okay. And this guy, the initial segments of this one are, again, 0, 0, 1, 0, 1, 1. So that's all good. 0, 0 is there. We haven't used the initial segment is 0. And I guess lambda has to be there because it's the initial segment of everything. What is lambda? Okay, look back. What is lambda? This is the empty tuple. Lambda refers to the tuple that is empty, as you could have expected, because this has to be a tree. And okay, so it satisfies the property, but then it's like, okay, it's a weird set of strings. What's about the property? Let's draw it. And why is it called a tree? It's important to draw these things. And how you draw it, well, I don't know. Let's try to draw it as a tree. So here is lambda, empty tuple. And then essentially you have two possibilities. And here we have tuple 0, tuple 1. And here is 0, 0. Let's see what else we have in here. We have 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1. We don't have 1. Yes, we have 1. It's right here. And then 0, 1, 1. We have 0, 1, 1, 1. And 0, 1, 1, 0. Correct? That's right. So we have those guys. Why did I draw it like that? Well, I guess I had an idea. If you didn't have the idea, well, maybe you have to try a little bit to see if it looks like a tree. Some people draw the trees growing down. But it makes sense. And then what is inclusion relation here is this one, right? So this one is a subset. It's including that one. This one is including that one. This one is including these two. This one is including these two. Okay, that's a tree. And the infinite binary tree, of course, you can think, keep on growing, but these are the only ones that are there. And it's closed downward. Okay, so the infinite binary tree will have continue going, no? Like these two, and then these two, and then these two, these two. And then from here there are two, and then there are two. And then from here there's one. And it keeps on going all the way up there, and this, what we call a tree is something that is closed downward. So it's a subset of the full binary tree. Okay, we understand what a tree is. Okay, so what does Koenig's lemma said, which is a theorem here, but it's well known as a lemma, Koenig's lemma, and it says the following: every infinite tree has an infinite branch. Okay, every infinite tree, I guess. Well, let's see what it says. In other words, if T is a subset of set of tuples, is a tree with infinitely many elements. Okay, so that's what it means, an infinite tree. That it has infinitely many elements, infinitely many of these guys inside. Then there has to exist a function from the natural numbers to 0, 1, which is the same thing as saying an infinite binary sequence, f0, f1, f2, infinite sequence of zeros and ones, such that whatever it says here, we have to look back and see what it means. F restricted to, remember this meant, we saw this in the last video, this means F restricted to 0 up to n minus 1, which essentially means, what does it mean? It means the tuple f0, f1, all the way up to f minus 1. Okay, so all this, you have to look back in the textbook to see what these things mean. So f restricted to this, so it's a tuple. So essentially you have this finite function such, and it has to satisfy that for all n in the natural numbers, if you restrict this function up to that n, so all the initial segments of the function belong to the tree. Okay, so these functions, these are all nested. So a path like that, if you want to draw it, it'll have to be like f0, f1, f2, f3, f4, f5. f6, and go up, continue going up forever. So that's an infinite path. And okay, so that infinite branch. So now we understand the first sentence up here, that every infinite tree, so that tree with infinitely many nodes in it, must have an infinite branch, something that goes up forever. Cool, that's a theorem. So let's think about it before we read the proof. Is it obvious? Well, an infinite tree, let me draw a different one here. Maybe it goes here, it continues, and then it splits, and then you have here a split. And it's infinite, it has infinitely many nodes. So we'll say, well, doesn't it mean that you can keep on going up because it's going to have infinitely many nodes? But the problem is that you don't really know where to go up, right? Because maybe this tree just ends up there, and you would say, okay, well, maybe that's not the right way. We should have gone this way. And then here there are two more, here there comes a tree, and then which way do we go? Well, I don't know, maybe come this way, and maybe the tree ends right there, and you say, oh, okay, I have to go the other way. So how do you build this function, this infinite branch that goes all the way up? It looks like this should be true, but it requires a proof. It definitely requires a proof. So let's see the proof. Again, we're applying compactness force intentional logic. So you expect what kind of proof is going to be. Let's see what it says. Okay, so we have a tree T. And what do we say? So for each n, let Tn be the set of all sigmas in T such that, and this means length. Again, so there's a section in this book about everything about strings where you will find all this notation. This means the length of the string. So this means Tn means all the sigmas that have length n. So think in this what it means. So length n would mean if n is up here, it means all the ones that have a certain length. Okay, so those are Tn. So draw the picture and think what these things are. So notice that each Tn is finite because it's exactly the set of strings that belong to 0, 1 to the n, set of n tuples of 0, 1, which is finite. It has 2 to the n elements, right? Since t is infinite, there must be infinitely many n's in the natural numbers such that Tn is not empty, right? Because each of them is finite, so if there are only finitely many of them which are not empty, then you have only finitely many elements, right? So that's why. Since T is a tree, and hence closed under initial segments, we know that if Tn is not empty, then Tm is not empty for all n below n. Okay, why is that? Well, what it's saying is that if we have Tm is here, and here is m below m, that's what it's saying, and Tn is not empty, so there is somebody here, then there must be somebody below, and that's because of the restriction property of the tree, so there has to be somebody below, right? So once you have somebody not empty, all the ones below are not empty. Combining these facts, it follows that Tn is not empty for all n in the natural numbers. Okay, so what is that? Well, what are the facts? Saying that T is a tree and hence closed. Okay, so whenever something is empty, all the ones below are not empty, and infinitely many of them, infinitely many n's are not empty. So we have infinitely many things are empty and they are closed downwards, the ones that are not empty, so it has to be everything. Okay, so remember, always stop and see each sentence why it's true. Okay, so that's what we know so far. For each Tn, which is each line like this, is not empty. Okay, so it's it's not clear yet why it's telling us this, but it's probably going to be useful soon. Okay, now we go into the usual format of the proofs of this form. Okay, so we are going to again define a set of propositional symbols or sentential variables, A sub sigma, where sigma is a node in the tree. So for each vertex of the tree that belongs to T, we have one of these A sub sigma. And with gamma is going to be this following set of formulas. How to look at see what each one says. So this one says disjunction, big disjunction. Remember, this means OR of all of this, and disjunction of these things. For all the sigmas in Tn, so for all the ones in here, but only the ones in Tn. So it's not everybody in that, it's only the ones that belong to T. So Tn, you have to make sure we understand what that means. It's only the ones that belong to the tree. Okay, and Tn contains this guy and this guy, and not the other ones that don't belong to the tree. So for each of those sigmas, we are considering a variable, the variable, sentential variable, A sub sigma, and it's saying one of them is true. Okay, so at each level in tree, one of them is true. And at each level of the tree, if you have two different ones, sigma different than T, they cannot both be true. So then the two of them are saying, so you have at each level exactly one of the A's is true. And then this one up here is saying that if you have sigma is an extension of tau, so if you have sigma up here, so look at the picture always, and tau up here, then if sigma is true, the A sigma is true, then A tau is true. Okay, so the set of things that are true, so unique at each Tn, for each level there is a unique one, and then it has to be closed downwards. So we can guess this, this is trying to get A sub sigma is trying to, so what are the A sub sigmas? Here it's not saying what A sub sigma is, it's going to come up later, so you can either finish reading and try to figure it out, or try to guess. And the idea is that a sigma true represents that sigma is in the branch we are trying to find, right? And these things up here says the branch has to cut each level exactly one place, and it has to be a branch, it has to be closed downward, right? So if you have this guy, you have this guy, all of these guys will be true, and it meets each level 1. Okay, so that makes sense. So let's see what it says. So we used compactness theorem to show that gamma is satisfiable, as we expected. Suppose, so we have to do what? Suppose that gamma 0 is finite. Why do we suppose that? Because that's what compactness, where we can use compactness. We have to show that each finite subset is satisfiable. Okay, so let capital sigma be the set of all the little sigmas that are tuples of which such that the variable a sigma occurs in the element of gamma 0. So gamma 0 is a subset of all these guys, contains only finitely many of these formulas, not all of them. So only finitely many of these variables occur inside. Consider all the ones that occur. Cool. Let n be the maximum of all these guys that occur up to there. Okay, so there are finitely many, so there is a level in the tree such that all of them occur only up to that level. Since Tn, the tree up to that point is non-zero, not empty, just take an element in there. So essentially what we're having here, let's go to the picture and see what's going on. So our sigma maybe sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. I don't know, they don't need to form a tree, they are only the ones that show up in gamma 0. And then n is the maximum that show up, so maybe this one shows up and this one shows up. Okay, so not all of them, but some of them show up in this set of... okay, and then let's say, well, since that one is not empty, there is something inside. It's not saying that tau has to be one of these sigmas. It could have been, because we know that there is n is the maximum of the levels of the sigma, so it has to be one of them, but it doesn't say that. So maybe this one is tau, or maybe one of the green ones. We don't know. And then it says, okay, define a truth assignment, which we're going to assign a value to each variable, and it's going to do the following. If sigma is the initial segment of tau is 1, and otherwise it's 0. So it's going to assign 1 to all the initial segments of this tau. This one, this one, this one, this one, this one, this one, and this one. Some of those appear in these sigmas, some of those don't. And then, so those red get 1, and all the other ones get 0. Okay, always drawing what you see. Okay, so you can see that's enough to make all the formulas in gamma 0 true. If you look at the formulas in gamma 0, you will see that, okay, it definitely satisfies all of these that show up in gamma. It satisfies all of these that show up in gamma. And it might not satisfy these ones if n is too large. But gamma 0, but for the n's that show up in gamma 0, this is true. Because gamma 0 only mentions n's, below this n. So the fact that we are not looking at the tree above it doesn't matter. Okay, so for gamma 0, for the finite set, all the formulas become true, not for all of gamma, but for gamma 0. So we get that gamma 0 is satisfiable. And now we can use compactness to get that the full set gamma is satisfiable. Make sense? Yes, so that's what compactness says. Okay, so what does it mean to be satisfiable? Well, fix a truth assignment that assigns every variable a true value, and remember, forget that this means false and true, which makes all the formulas in gamma true. Okay, that's what it means to be satisfiable. So notice that for each n, there is a unique sigma in Tn such that this is true. Why is that? Well, because in the first two set of formulas in gamma say exactly that, and you have to look back, see what they say. They say exactly that at each level, exactly one of them is true. So for each n, denote the unique sigma, that unique sigma, by rho n. And notice that rho m less is the initial segment of rho n whenever m less than n. Okay, so what does that say? So it says that the chosen one for level m is below n. The chosen one for level m is below the chosen one for level n, and that's because of the third clause of the third sets of formulas in gamma that says that if this one is assigned true, then initial segment is assigned true, but a unique one is assigned true. So it has to be this one. Okay. And now we can define this function by essentially putting all these guys together. So what f of function from natural numbers to 0, 1 by letting f of n be rho n plus 1 of n. And here you will be, okay, wait, what does it say? Well, okay, so these rho m's and rho n's, these are tuples, finite tuples. And what we want to define is a function. What is the value of this function at n? And why is it taking n plus 1? Well, because rho n has size n, so it's only defined from 0 to n minus 1. So you need to go at least to rho n plus 1. And then you may say, wait, why don't you just, what happens if you take a bigger rho, like for something bigger than n plus 1? Well, they are all nested. These guys are all including each other. So it doesn't matter which one you choose. I mean, they are all a subset of each other. So you will get the same thing. Good. We then have that f up to n, which is essentially rho n, right? So the initial segment of f up to, this was defined exactly these ways, right? Because for the smaller numbers, they are all initial segments of rho. And rho n belongs to t. So we get that all initial segments belong to t. Okay? So it takes long. It takes a while to read a proof, as you can see. I mean, you have to stop at every line and be, why is this line true? And then read the line, why is this line true? So it takes some time to read the proof, but that's the way you should read the proof. And sometimes the notation is not clear. You have to go back in the textbook and find the notation. But yeah, that's how you read math. It takes a long time to read just something like this small. Okay, so that finishes the proof. So we build a function that was the branch that we wanted on the tree using compactness. Compactness allows us to kind of find full truth assignment. See you in the next video.